Nice to be here again. My name is Stritzinger. Not working? Test, test. Oh, just go closer. I hope it doesn't misbehave again. So, does it work now? Okay. Yeah, nice to be here again. Last time I've been kind of like getting the nickname, oh, you're the Erlang guy. Today is not about the Erlang, but I cannot promise that you won't be exposed to Erlang code because that's how I write my code. So it's about mapping processes to nodes. So normally we do this manually. We decide like what runs where. So we have like a bunch of processes, which could be also sequences of tasks or whatever, you name it. And we have a bunch of nodes, and we decide what runs where. But we want to take that away and make this automatically. So basically, when we have this network here and that communication graph basically between the processes, we want to automatically map them in an optimal way to the nodes. Why do we want to do that? So I'm in IoT for quite some while, and what I've seen over and over again is basically a very early architectural lock-in, because you need to make the decision what runs where a priori. Often you have to use different programming languages to write the different parts of the software on small IoT nodes, on gateways or cloud computing. And then when you run the thing, you figure out like, oh, this was all a mistake. We should have taken this part over here and that part over there. But now it's too late because you're locked into the architecture. Also, you want to have architectural flexibility because not always basically architecture stays the same. You get basically an extra node or get extra compute on premises because you added it because you think like everything will go faster or the cloud cost is too high or something like that. And that's what you can adapt to then when you map this processing to the nodes, basically to the network automatically. And also you can use all the resources on the edge of your network, can use it in an optimal way. It allows to really use all the stuff because you don't need to be very over careful that you don't put too much compute on the small edge devices because the system would adapt to the actual availability of computation. And it also makes your system less complex because you only specify your user intent of your data flow graph, for example, and what you need, your latency needs, etc. And the system is actually solving all these complex problems for you. So how does this look in space? In the general system, we use a lot of criteria. So I picked a few that are more space relevant and different than on some applications in the ground. One observation is that the power limitation kind of like goes for both communication and compute. So you both drain the same power and you need to make the decision, do I compute more and send less or do stuff like that? That makes the whole problem more interesting. You have the similar thing in small IoT nodes that run from battery or energy harvesting. But in most of the applications on the ground, you have enough power to actually not have to think about bandwidth and compute bandwidth at the same time in a joint way. Latency is much more visible in space than on the ground, unless you're in LEO. On the ground, we basically most of the time we ignore the latency. Oh, it's a few milliseconds here and a few milliseconds there, until all our microservices add up to a lot of milliseconds, and the user complains that it's too slow. But then it's also too late. We should have looked at latency early on. Except when we do hard real-time stuff, then we look at latency. But in space, it's much more obvious because if your latency is measured in minutes, not in milliseconds, then it's much less ignorable. We have constrained memory, so as well persistent memory as RAM. So kind of like everything needs to fit. We cannot like store infinite amount of data, so we need to do something about that. And then there's always, in any case, the proximity of like sensors. If you have a node that reads the sensor, it needs to sit on a function that reads the sensor. It needs to sit on the node that actually has the sensor connected it to, because otherwise it wouldn't work. And so how do we do that? How do we actually map this one graph to the other? So graph mapping is well, pretty cutting edge topic still. There's a bunch of researchers, but not too many looking at that. So one of the most common ones, because it has some graph theoretical relevance, is a graph retraction, which means that you map a graph to its own subgraph, which is an example here. That's an example from Wikipedia. Basically, the inner circle, the inner pentagram, basically, not pentagram, the inner five-corner thing, is basically the thing it's mapped to, and all the other things are mapped to on the thing. But you see that edges only get mapped to edges. So there's never an edge between two nodes in one node. But actually, when we map computation, that is often the case, and it's actually favorable, because if I have a communication edge and stay on the same node, it's highest bandwidth. It doesn't cost me much, so it's actually something you want to. So we expand this whole theory of like graph retraction into a generalized graph retraction, that you map one graph to a subgraph of another graph. And also that we allow basically edges on the same map node. So what we need is an algorithm to find this optimal graph retraction to all our criteria. So it needs to be satisfying all the criteria, so we can't use more memory than there is there, for example, or we can't use more energy than we have. And then there's also kind of like general optimization things, that there are better solutions and worse solutions. And also what we can do, if a solution is not possible because nodes are too far apart, we can automatically insert nodes in the middle as a proxy node, basically to forward a node, and I'm getting to that later on. The whole problem is NP hard, so that means it's kind of like exponential, and computer scientists like to say, oh, it's impossible, it's NP hard, but there actually is a lot of useful solutions for NP hard problems. If you don't want to find the optimum, but a optimum or a good enough solution. The search space is pretty large. It's n to the power of p, like n is the nodes and p are the processes. So that's even more than factorial. Well, that's not in our favor. So we need to look at a bunch of solutions. I was actually very happy that somebody mentioned SMT solvers this morning, so I don't have to explain much about them because you already heard all about it. Very useful. So that's kind of like a spectrum from more precise methods or exact methods like SMT solving, integer linear programming, divide and conquer is already getting fuzzy because there it depends on like how you group things into like clusters of graphs and then optimize that. So there's manual intervention necessary also for heuristic search. What you need is a good heuristic, which is the hard part of heuristic search, finding out a good heuristic. And that is also a lot of like hand tuning involved. And then we have like the more generalized methods like simulated annealing and genetic algorithms, with genetic algorithms being the most general one. So let's look at SMT solvers. Well, I tried them last year and they didn't work. At least that's why I wrote naive SMT, because there might be some SMT solver expert that can actually make it work. But I think that the underlying, that we can only push the envelope. So the graph that we see, it was a very simple mapping. I mapped basically 10 processes to 5 nodes, or 12 processes to 6 nodes, or 14 processes to 7 nodes, and it was only a ring. So it only needed to find the solution to wrap the ring twice around. That was the optimal solution. So it was a very simple problem which could be hand-checked. But you see, while the runtime, so the runtime was seconds, is very low in the beginning, then it goes to a few seconds, and then, well, I gave up on that. So one more step, and it didn't finish. I used C3, and maybe one little thing about SMT solvers, since they seem to be a topic today. There's also another way to the Python binding. There's a kind of like a standardized way to describe this problem to these solvers, which is Lisp-like, like lots of brackets, and it's standardized, so you can actually use the same description and try it out in different solvers. So that's also a thing to consider when you want to look into SMT solvers. So currently work in progress. I'm working on genetic algorithms. So I went to the other extreme of the spectrum, and in the end, I want to try out different things. It's inspired by evolution. So what you do is basically you start with a bunch of random solutions, and then you select the best ones. and you cross them over basically. So you make mixes of two good ones, and you also now and then you kind of like do point mutations on solutions to actually get more variability into the gene pool. It converges slowly, but it converges. It's very robust. It usually always converges. And all you need is a goodness function, basically, and then you let it have at it, basically. You need to map it also to the crossover points or whatever, but that's pretty trivial. It's very parallel, so it's either an ideal fit for multi-core CPUs because you can evaluate multiple solutions at the same time. And it's also distributable. So you have independent populations on different nodes, for example, which can be quite apart. And what you do is basically every now and then you let a bunch of species migrate over the mountain path and go into the other node and swap species basically, and then you can basically arbitrarily scale it up. Why we like distributable algorithms? Well, we build a distributed computing infrastructure from cloud to edge. So I like everything that's distributable because we can scale it like hell. We kind of like made the orchestrator for that. And we can also push it into the edge, basically use all the compute power at the edge. So let's have a small demo. This thing comes up. I actually want to get out of my slides. So the demo is very quick. First, let's look at some code. So yeah, there's the Erlang code. So we have basically a bunch of records where we model our nodes. So we have an ID, which can be anything. And what we model is basically, we model the available power in watts, like just a rate, MIPS per watts. That's how much computation costs us and how much memory we have. And then on links, we also have basically the megabits per second per watt or bits per joule or something. And the max bandwidth and what they connect to. So it's a very simple model, and it models basically the processes and the nodes. And if I, well, that's a very simple kind of like optimizer. So we have penetless for everything. We have the goodness function implemented, and because actually for small examples, which is the only thing I can show in a demo, actually brute force is faster than genetic algorithms. So I actually run the brute force tester, which I, of course, also built at first, because actually I don't want to make you wait for the larger one, for the longer one. So let's make this big. I'm building that little project, and basically there's two different samples. One has only 2 nodes, compute nodes, and 2 processes. That's S1 here, and with all the values set basically. So we try that for first. S1. Oops. Where am I? Mistyped. No. No. Such a simple demo. Why does it not work? Oh, start demo. Oh man. Well, yeah. So in this case, the simplest solution basically after very few trials is basically everything gets mapped to one node. So the processes are numbers above 10 basically, and both are get mapped to node 1 because not having to communicate and both fit on node 1, it's the best solution in this case. And if you do a little bit larger one, where we have basically 4 nodes in a square with different bandwidth and different memory things, and I have basically the processes mapped to these, and there should be one good solution, which is incidentally basically process 11 gets mapped to node 1, process 12 gets mapped to node 2, and process 13 to 3, and 14 to 4. So basically we map the circle on the circle, and you see that the goodness function is highly variable in the middle of it. So that's all of the. Get rid of this annoying thing here. And go back to the slides. So, so far we actually made it a little bit more simpler, our life, because we had basically a static graph of a topology where everything is defined as rates. So there's a message rate and a bandwidth, and we map that. But in reality, especially in space, we also have scheduling problems that we can't send it every time, and that our life is much more complicated because we have the time dimension to think about. But if you have this topology, the static topology, and you spread it out along the time axis, then I didn't do anything. You spread it around along the time axis, you see then basically in the top layer, basically all these three nodes can still communicate with each other. In the lower one, basically the communication broke up between a few nodes and only N2 can send, whereas the other twos can send along. And if you do the same thing with the processes, we basically also put a timeline and split up the process and sync the tasks. Then we just have two more complicated graphs to map to each other. So it's a harder task to solve. So we actually want to be able to solve really large graphs for that. But we can actually also solve the scheduling problem and the placement problem at the same time, which could be extremely useful. So since we have these algorithm problems, basically SMT solvers don't scale so far, and genetic algorithms, and we want to compare all these solutions and maybe in the end build a hybrid solution that actually combines the different things for different scales. What we're actually missing is a benchmark for that. So actually a good collection of real-world data flow graphs and real-world topologies and with real-world data to map them onto each other. So that's kind of like the question to the audience. If anybody is willing to share any interesting graphs with us, I'm actually building a benchmark seed out of them at the moment. There's a bunch of like topologies that are kind of like recurring, just to show them. Basically, we have aggregation where everything flows together. We have dissemination where everything gets put apart. And then we have kind of like a MapReduce thing where it goes apart and then you collect the result again. And there's simple static data flows and request response on the side. So where do we get these data flow graphs from? One way is you program in a data flow paradigm, like you use MATLAB anyway. So you actually get the data flow from MATLAB maybe. Or in this case, this is a PLC programming language that we happen to have a compiler for, that you basically annotate your stuff in the graphical world already. But there's also other things. There's ONNX models, which is a standardized way to share machine learning neural models, which are basically also a graph inside, which have the different layers of the network and which allows you to split up your network and then place the first layers already on your edge node or in your satellite, and then have more beefier nodes to the rest of the layers and make sure that basically the communication is narrow at the point where you split up the network. So we can do that. And of course, you can model everything as data flow in the end. There's also, I'm running out of time, but I'm almost through. A thing which we are thinking about, like, for example, for aggregation, usually you have the task, I want to aggregate all these sensors into one value, an average or whatever. But you have multiple, a hierarchy of nodes between here and there. And what you in practice want to do is basically you aggregate a little bit on every node or everything you can aggregate, and then you spread out the aggregations through the network. And by doing some kind of like composable graph transformations on the data flow graph, we can actually automate that these nodes are spawned in. Also, one thing which we're currently working on is kind of like the security aspect. If you have like untrusted nodes and you want to send some data through that, we can automatically insert an encryption and decryption on both ends, basically, before it goes into the untrusted network. And that is it. That's the last slide. So part of it was funded by this new project, which looks at the security aspect of the whole thing, the trust and sensitivity. And therefore, I have to mention it.
All right. Thank you, Pierre.
I'm happy with it.
Any questions? I don't have anything online. There's one here.
Hi, this is going to be a pretty naive question because I don't know much about the field, but I was wondering what prior art exists. It seems like similar problems were probably faced by people operating server farms, constellations, other things. So what other approaches are used for mapping work to nodes?
I found a bunch of like specific solutions for specific problems using similar things like, oh, how we did this on this mission, we automatically used the SMT solvers for doing that. I found these kind of papers, but I did not find any generalized solution. But that was just me not finding it. But well, I'm industry, so as long as I don't find a competitor, that's fine for me.
Thank you. Any other questions? We can take one more. All right, that's it. Thank you, Per.